Hi, so this is problem 4.1 at page 211, and this is a practice problem for applying conservation of mass. So in this problem, we are told that we have an 8 cubic feet tank contains air at an initial temperature of 80 degrees Fahrenheit and initial pressure of 100 pound-force per inch squared. The tank develops a small hole and air leaks from the tank at a consistent rate of 0.03 pound mass per second for 90 seconds, until the pressure of the air remaining in the tank is 30 pound-force per inch squared. Employing the ideal gas model, determine the final temperature in degrees Fahrenheit of the air remaining in the tank. Alright, so the first thing what we want to do is we want to write down what is given to us and what we need to find so things can be clear. So first thing, we are given a volume V of 8 cubic feet. And we have a cylindrical tank. Inside this tank we have a fluid which is air, so we're dealing with gas. And since we are dealing with gas, remember that gas occupies the whole volume because gas molecules are free to move anywhere inside the volume. So the volume of gas at state 1 or initial state, it will be the same as the in state 2 or final state. So here at state 1 of air inside the tank, or you can say state at or initial state or state at 0 seconds, because remember that's the state at 0 seconds before the air starts to leave or leak from the small hole. And the temperature will be 80 degrees Fahrenheit and the pressure will be 100 pound-force per inch squared. And after that small hole being developed, it will have a constant mass flow rate at 0.03 pound mass per second. The air flows from the small hole for a time period of 90 seconds. So at 90 seconds, we will have our state 2. So state 2 of air inside the tank, the pressure is 30 pound-force per inch square, and we are asked to find the temperature at state 2 in degree Fahrenheit. It's a very good practice to draw and sketch your problem. It helps you visualize what is given, what you need to find, and the approach that you can use to solve this problem. So here let's draw this cylindrical tank which have air inside it, and at state 1 or at 0 seconds we have these two properties, the temperature and the pressure. When the small hole developed, the air start to flow for 90 seconds. So at 90 and it flows at a constant mass flow rate of 0.03 pound mass per second. At 90 seconds or state 2, the pressure is 30 pound-force per inch squared, and we are asked to find the temperature at state 2. And here E is the subscript, which means exit. Now, it's a very important thing to do whenever you sketch a thermodynamic problem is to identify your system and the type of system that you're dealing with. To do so, to identify your system is by drawing the boundaries of the system. All right, so this right here, this dashed line represents the system boundary. Anything outside is considered the surrounding. Anything inside is the system. And the system, bottom line, is what are you interested in studying. And here we are interested in studying the air inside the tank. And now this type of system is control volume. Now you remember that systems have three types. We have closed system. Closed systems does not allow the mass flow rate or exchange of mass. So it's not a closed system. It's not an isolated system. It is an open system. So we can use control volume or open system interchangeably. So next, what we want to do is we want to see how can we solve this problem. So we are told to employ the ideal gas model. So right here is the ideal gas equation, which is pressure volume equal to mass times R times T, and that's at state 1. And that will be the equation of state or ideal gas equation at state 2. Awesome. So at state 1, we have the pressure, we have the volume, we can find the R from a reference table, we have the temperature. So from this equation, we can find the mass of air at state 1. What about the air at state 2? We are given the pressure with the same volume. We don't know the mass. We know the R now. The temperature is what we need to find. So this is one equation with two unknowns. I wonder if there is a way we can find this mass. So here we will apply the conservation of mass to find mass at state 2, because the conservation, this is the equation that represents the conservation of mass principle. The change of mass within the control volume over a period of time equal the mass flow rate in minus the mass flow rate out. So obviously in this problem, the mass flow rate in is 0. So here what we can do is we can solve for the change of mass within the control volume. And remember, the change of mass within control volume, what does that mean? It means the change, the difference between the mass of air at state 2 minus the mass of air at state 1. And since we know the mass of air at state 1, we can find the mass of air at state 2. All right. So in this slide, what we will apply the conservation of mass. Remember, this is the equation that represents conservation of mass principle. And remember, we told that the mass flow rate inlet we don't have, so that will be 0. So we can rewrite this equation to be the change of mass within control volume over a period of time equal to minus the mass flow rate exiting the system or exiting the control volume. The minus sign, it means leaks out, or that the mass flow rate is leaving the control volume or the system. So here we can plug in the data that we have. So we know that the mass, the delta time based on what's given to us is 90 seconds. That's the amount of time the mass took to leave the system. And the constant mass flow rate given to us as 0.03 pound mass per second, and the minus sign, which indicates that the mass flow rate is exiting the system. So here what we can do is we can solve for the change of mass within the control volume by taking this 90 seconds, move it to the other side of the equation from division to multiplication. So here the second will cancel with this second, and we will be left with the pound mass. So the change of mass within the control volume is equal to 2.7 pound mass, and the minus, it means that that's how much mass have exited the system. And we can rewrite this equation as we mentioned in the previous slide, that the change of mass within the control volume is basically the final mass minus the initial mass within the control volume. So the final mass is m sub 2 minus the initial volume m sub 1. Or in other words, the mass at 2 is mass at 90 seconds, or mass at 1 is mass at 0 second. All right, so in this slide, what we want to do is we want to employ or use the ideal gas law equation, and in this slide we will use this for state 1, or the gas at 0 second before the gas starts to leave the system from the developed whole. So this is the ideal gas equation. So here the pressure in blue, that is something that is given. The V is given. We need to find the mass. The R in green, that is something we can get from a reference table like this one here. And the temperature is also given. Now regarding R, we will use definitely 53.3 because the units in here matches what we have in the problem statement. Now we can rearrange this equation, so mass will equal to PV over RT. And here make sure that you convert the correct units, or use the correct units, sorry, to match the R value that you have. So here you have inches squared, we're gonna change inches squared to feet squared. Yeah. And instead of using degree Fahrenheit, we're gonna use degree Rankine. And this in purple is your conversion factor. And as a practice, what you can do is you can make sure that these units cancel each other, and you will end up with pound mass. And you can use this and you can do this by yourself as a practice. So when you plug this into your calculator, it will give you that the mass at state 1, or at 0 second before the air starts to leave the system, is 4 pound mass. Now we can use the equation from the conservation of mass from the previous slide and plug the 4 pound mass in, and that will help us find the mass at state 2. So mass at state 2 will be 1.3 pound mass. All right, so in this slide we will deal with air at state 2, or air at 90 seconds. So again, the pressure is given, the volume is given, the mass we were able to find it, awesome. R we extracted from a table, and here we want to find temperature. So now we're gonna solve for T. So T will be PV over MR. Again, plug in the correct values and make sure to use conversion factors, and make sure that the units cancel each other to give you the unit that you want, and the unit we want in here is degree Rankine. So when you plug this into your calculator, it will give you 498.77 degree Rankine, but we are told to find it in degree Fahrenheit, so we will use the conversion factor that we used in the previous slide, but instead of adding we will be subtracting, so it will give you 39.08. Thank you very much. Have a good day.